Okay. We're going to use work energy to solve this problem. We have an incline in an angle, depends on your ABC numbers. Frictionless incline. So the length of this thing is A meters, whatever your A is. Want to find the net force. It's the first thing you want to do. Then, having found the net force, you don't find the acceleration. You could. And that's a good way to check whether you did it right or not, because you can do this with acceleration. But it's a lot simpler when you use work energy. Okay. And there are other insights that come from work energy. We're going to try to see what some of those are. Okay, well, if you find the net force, then use the work energy theorem to find VF, provided V naught is this, and then again, but again with V naught equals something else. Okay. First thing we do is draw a free body diagram. That much ought to be so automatic that your hand does it without your brain even thinking about it. That's badly drawn, you know, this projection line is parallel to the y-axis. You still get the idea. And what we have here is mg. Okay. We place mg by mg what? Well, here is our angle. Call that angle theta. Then that's going to be mg sine theta, because you've got a triangle here with theta side opposite is here, which is identical to this, because this is all a rectangle. It's a parallelogram, but it's a rectangle in this case. So you see that, you know, this is identical to this, and in the triangle here, that's opposite your angle theta. And there's your magnitude, there's your hypotenuse, just hypotenuse times the sine of theta. Straightforward right angle trigonometry. Alternatively, you could measure your angle around here, it'd be 270 degrees plus theta. And then you could do mg cosine theta here, and mg sine theta here, and the plus and minus signs would be taken care of. And sometimes you want to do that, especially when the plus and minus signs get a little confusing. You should be able to do it either way. And over here, of course, you got mg cosine theta. This is times your I vector. It's then the negative of this. Leave myself room to write the J vector, but we don't actually need this. Okay, so that's a pretty sloppy diagram that you can draw your own. Okay, and then of course, then we have the normal force perpendicular to the incline. There's no friction, and there's no acceleration in the y direction. So this happens to equal this. But that's not important. These two just add up to 0. Okay. And the net force is mg sine theta times your I vector. And I want you to use the I and J vectors. And you just really need to get used to that, because pretty soon we're going to start using dot products and stuff like that, which you should know from the review. Okay, so how do we apply the work energy theorem? Well, first we have to know the work energy theorem. We have to know that work is change in kinetic energy. And I would write it this way, then I would say I want to write this with a dot product, but I think I'm not going to this time. F net delta S 1/2 MVF squared minus 1/2 MV naught squared. Okay. Now this is really a vector dot product, a dot product of your F net with your delta S vector. But in this case, I can say that I kind of slop that down, but I say F net and delta S are in the same direction, so we can write this. Okay. So this becomes pretty easy. We have mg sine theta times mag meters equals this. That's a little sloppy because you're putting in numbers and so forth. So you might not even want to substitute your A meters here. You might want to say, okay, I'm going to cut across this. I'm going to do it simple. You'll say F net is mg sine theta delta S equals 1/2 M df squared minus 1/2 M V naught squared. Not cluttering it up with our given information, using symbols for everything. Okay. So how are we going to calculate VF? Well, do we know V naught? Yep. Do we know delta S? Yep. Do we know theta? Yep. Do we know M? Nope. Do we have M on both sides so we can divide it out? Yep. S doesn't matter. Okay. So I guess we can over here do the rest. So again, we have if V naught equals 0, then VL is the square root of 2 mg sine theta delta S over M. And it's plus or minus. We have to consider both plus and minus solutions. Okay. Now, if you plug the messy numbers into this thing, it's messier than this, because this ends up being fairly simple. And then what that equals depends on your numbers. You've got your delta S, you got your angle, and there's no M there. And of course, you know what G is. Simple enough. You want to memorize that as a formula. I mean, that formula pretty much applies anytime you have an initial velocity of 0 on a frictionless incline. So you can memorize that as a formula. You can derive 10,000 formulas and memorize them all so you don't have to think about anything. It's much easier to think it through than to memorize a bunch of formulas. Some formulas you need to memorize. Some formulas you just kind of need the memory to check with your analysis. You analyze it and you see if you get what you think the formula is going to tell you. Okay. And then you also want to do your dimensional analysis. We only have two quantities here that have dimensions. You got G, which is in meters per second squared if you use SI units, and delta S in meters. So you have meters squared per second squared. And the square root of that is meters per second, which is a unit you need to have. So now you don't have to write down a bunch of units. Although you probably want to use units when you plug in here, just to be sure. Okay. So you do your dimensional analysis off to the side. It's going to have units of length for time squared. Units of length, so you get units of length squared for time squared, which is units of velocity. Like in terms of SI units, meters per second. I really recommend that you put units in when you do this, just to double check. But you don't want to write the thing out. I wrote meters here. And all of a sudden I had units with a bunch of stuff that doesn't have units specified. It's a little more elegant to do it this way. I did one last week where I did that to try to make a point, and the units ended up just being confusing. Okay, that's my bad. It didn't work out, but it's really easier to see the symbols. Okay, so there we have this. The next complete solution. What do we use? What principles do we use? What principle did we use here? We used Newton's second law, basically. Okay. And of course, we used the principle that forces in the x direction are linearly independent of forces in the y direction. So you have a basis there. Put it in terms of linear algebra, for those who haven't had linear algebra, we use the fact that a force in this direction has no influence on a force in this direction. They act independent. So that the accelerations act independent, so that the velocities are independent, so that the positions are independent. Okay, it all comes down to forces are independent. Now that's one I don't think I put on here. Maybe I did. Yeah, I put fx, fxy, and fx, fy, and fz are linearly independent. That means just what I said. They're independent of one another. Okay, everything that happens in the x direction is independent of what happens in the y direction, the z direction. Strictly, that's not necessarily the case because you have air resistance in the x direction that affects the time it takes things to happen, which influences the quantities you have in the y direction. But the forces are still independent. Okay. So that can be a little confusing, but we deal with it. Okay, so that's just one illustration of how the work energy theorem gives you a very simple result very quickly. You just do the free body diagram, get the forces, write it out. In 2 steps, you've got this. Now you could have gone and found the acceleration, figured out the final velocity, and plugged it into 1/2 mv squared. Or what we're looking for VF. So you could use the equation of motion to find VF. Okay, it's not that much harder, but why bother with acceleration when you can think in terms of work and energy? Because you think in terms of work and energy a lot more often than you think in terms of velocity and acceleration. One illustration. What if the graph is curved? Okay. Well, you're going to get the same result. Okay, so let's say we've got a curve graph. frictionless. Well, now you can't find the components of F and Y, of the force in the X and the Y directions, because it's going to keep changing. And your X and Y directions are going to keep changing, keep having. You can't keep rotating that coordinate axis, those coordinate axes, and expect to get anything useful. Well, what you can do is you can say that you have a certain displacement, okay? You have a delta Y here. And you can say that, okay, I've got my vector MGJ, horizontal vertical coordinate axes to indicate that now we're dealing here because your displacement compared to here is delta Y. And now how much work does this force do as you displace delta Y? Well, your delta S, and instead of delta Y, I'm just going to call this H. And H is not going to have the direction of delta S. It's going to be negative H times J. Your force okay, I'm going to pause a second and see if I really want to say this because it goes a little beyond what you've seen so far. Okay, I had to think a minute about how I'm going to say what I want to say without having done the next chapter, okay? So I'm going to take the net off of this. Say that F equals negative MGJ. It's going to turn out that this is the force that does all the work. Because the only other force that's acting here is going to be the normal force, which is perpendicular to your direction of motion, therefore does no work at any instant. And that's a little bit of a splash. Okay, so over here, one thing I didn't do here, and I really should have. When I talked about the work energy theorem, it's work by the net force is equal to changing your kinetic energy. Okay. So this is not work by the net force. This is not the net force. Well, the work done by any force is the dot product of that force and the displacement, or the integral of that force with respect to displacement. And we haven't gotten to using integrals now, but we probably will by Wednesday, okay? So here's your work done by the force F, not a net force. Make sure we'll see that dot. Well, that's MGH times J dot J, and J dot J is 1. This is incidentally a formula for what you call potential energy, and everybody uses when they shouldn't. Don't like that formula. tungsten principles. You're going to see it anyway, so I can't go into my lab and edit it on. Can't go into the textbook and edit it out. It's a great textbook. I still don't like that formula. If you want to like it, okay, just don't misuse it. Okay, I would like the formula if people didn't apply it, but it doesn't apply. In this case, it does apply because G isn't changing from the top of this thing to the bottom in any measurable sense, presumably. If this incline is 300 miles high, then G is changing, and that formula just doesn't work. It doesn't work when you put a satellite in orbit, because G keeps changing. But close to the Earth's surface, G is constant. We can get away with this. Only close to the Earth's surface. You can lock that in now. We'll save you time later. Okay, so that's the work done by this. Okay, now what about the work done by the net force? Net force at any point is this. And of course, we're assuming no friction because that's what we've assumed from the beginning. So it's the same problem as before, but it's on a slope ramp. Okay, so this is your net force. It's the work done by negative MGJ, which we calculated as MGH. Plus the work done by your normal force. Now, let's talk about how much work the normal force does. F norm is perpendicular to the incline. Delta S is parallel to the incline, okay? And actually, I'm going to say ds. Delta F would be a finite displacement. ds is your infinitesimal displacement. And your infinitesimal displacement is always in the direction of the incline. It's always parallel to the incline. Okay, say that delta S is parallel to the incline. Well, delta S is a very small increment of motion. That's almost true. But in the limit, as you approach your ds, it is absolutely true. And that goes back to calculus, theory of limits, and everything you really want to understand in life. Okay, so this is parallel, this is perpendicular. So the two vectors that are perpendicular have zero dot product. Go back to your definition of dot product if you like. Okay. Magnitude of this times magnitude of that times the cosine of the angle between them. What's the cosine of the angle between these things? They're perpendicular. What's cosine of perpendicular angle? Circular definition. Cosine's up, or the angle this way, and the x-axis is this way. Projection of the vector on the x-axis is 0. There's your cosine is 0. You really want to have that picture. You always want to have that picture. When you see a sine of 0 or sine of 90 degrees or 270 or 180 or whatever, or cosine of any of those angles, you just visualize the unit circle and understand the cosine is the x component, the sine is the y component, and you immediately know whether it's 0 or 1, the negative 1. Okay? You just emblazon that picture in your mind and use it every chance you get. Then you don't have to do much thinking. You got the picture, you know it's true. You don't have to memorize a bunch of formula. Although again, I don't have an objective to memorizing. As long as you memorize correctly and apply them correctly, but the picture is so much simpler. Okay, well anyhow, that's a little digression. Well, the work by F, and that's the work by our negative MGJ, which we just calculated to be MGH. We just put these ideas together, not difficult ideas at all. If you understand dot products, certainly you need to understand dot products, okay? They're simple. But you have to remember what they are, remember how to calculate them from the components or from the angle, from the vectors. Know that the dot product is equal just the product of the magnitudes. The vectors are parallel. They're vectors in the same direction. The negative, they're in opposite directions. It's all going to be really important. And 0 for perpendicular. Simplest test for perpendicularity of two vectors in 3 dimensions or 2 dimensions is dot product of 0. Okay. Okay, I notice that people are worrying about what's going on the inside, and it's natural you do that because you can't read my mind. And my mind was not clear enough on the fact that V naught X, V naught Y are here, right at the end of the incline. So that you're only dealing with what happens from here to here. Okay. So now you start with the net force equals change in kinetic energy. And then you start filling things in. See what you get. There are a couple of twists in here that you might or might not get, but let's just see what at least one side of the work energy ought to be pretty clear. The other side, we'll see. Okay, we're doing fairly well here. A couple little glitches, but here's where we start. Okay, well, work with the net force is I'm going to write this as F net dot delta S because we're in 2 dimensions. And the change in kinetic energy, of course, is 1/2 mvf squared times 1/2 mv naught squared. Now this side is really easy. Your net force is negative mg times your J vector. And that's dotted with your delta S, which is negative H times J. Same as it was in the previous example. But you can see that independently. You got mg acting down. Implicitly, J is up and I is to the right. Okay, so you got mgj minus hj because, of course, your displacement from here to here, you're going this way at distance h, it's going to be negative h times your j vector. Now we can already see that your right-hand side has m as a factor, your left-hand side will have m as a factor. So M is going to divide out whenever you want it to, but we'll wait till the next step to do that. So we have 1/2 MVF squared. The only thing we don't know is VF at this point. And that's what we're trying to find. So that's our unknown. That's our target variable, if you would call it that. Okay. What's V naught? Okay, there's a question. Let's discuss this. And if you already know, don't say. Okay. We know about V naught as V naught. You know where we are here. We've got this and this is really obvious. This is pretty obvious. Here's your target variable. What does that do about V naught squared? So V naught vector, we know the components of V naught, so we know that V naught equals V naught X I plus V naught Y. Okay. Okay, but what's V naught? About the magnitude of these. Now, there are various ways you can do this. The book's going to say, well, you got this component and the result is this way. So you add the squares of these components and you get the square of this. So you use the Pythagorean theorem, right? That's just fine. I'm going to get used to dot product and stuff, so I'm going to use a dot product definition. But I would expect you to use the Pythagorean theorem, say it's a square of V naught X squared plus V naught Y squared. Okay. And I'm not even going to put it in here because I don't have room. But now we can say that, okay, when we do this dot product, we get MGH. Then we have plus 1/2 MV naught squared, right? Again, this is not the vector V naught, it's the magnitude because you don't square vectors. But we do. And again, the Pythagorean theorem is fine. If we do V naught dot V naught, we end up with the same thing we would do. Okay. So I can say the theorem is okay too. You got V naught X, V naught Y. And V naught, right? That's a hypotenuse triangle with sides V naught X and V naught Y. So very straightforward. That product can be very useful sometimes. So kind of worth illustrating. Either way, you're going to get the square root of V naught. Well, you got to get V naught X squared plus V naught Y squared. Okay, so I'm finally going to get rid of that M on the factor. Everything. I don't even really bother writing V naught as a square root of V naught X squared plus V naught Y squared. That's right. V naught squared is V naught X squared plus V naught Y squared. That's your Pythagorean theorem. Okay. That's really what you're probably going to think, but I want to illustrate. Okay, well, at this point, just multiply by 2, take the plus or minus square root. Okay. I'm just going to write etc. down here because are we out of time already? I'm just sneaking. Okay. Newer. I was questioning on this, and you're right, I divided out all the M's, but then I wrote one down here and it shouldn't be there. But that would make the whole thing dimensionally consistent, so if you, inconsistent, so if you happen to do something as boneheaded as what I did, if you check the dimensions, you'll probably find it and correct it. If you don't check the dimensions, I'm not as sympathetic when I'm grading. Okay.